Hello everyone, I'm going to use this animation here to show you the propagation of what is called a simple periodic wave. This is the same website that I've used in class before to show you a couple of other simulations involving individual wave pulses. In this particular case, the little hand here that you see is going to begin to oscillate up and down in simple harmonic motion. When that occurs, it then sets the medium essentially into simple harmonic motion as well, but you end up with individual simple harmonic oscillators, each piece of the medium, for example, as being slightly out of phase with its immediately adjacent counterparts. This then results in the propagation of a simple periodic wave, which could easily be described mathematically as a propagating cosine curve. Okay, and then just in the other animations that I showed you in class, they're going to focus in right over here on this red dot and then plot its position from this equilibrium position as a function of time. We're not really concerned about that graph, however. We're instead much more concerned with the actual waveform here on the string itself. All right, so let me go ahead and set this into motion like so. And then the hand here is oscillating up and down in simple harmonic motion. This then sets each individual piece of the medium into simple harmonic motion, but all of the individual oscillators here are slightly out of phase with their immediately adjacent counterparts. Okay, let me go ahead and then freeze it in place, for example, like so. And then mathematically, there's really no difference between crests and troughs, but the crests are the top portions of the wave, and then the troughs are the bottom portions of the wave, like so. The distance from crest to crest is the same as the distance from trough to trough, and that's referred to as the wavelength. Okay, then let's say we had an individual observer standing right here watching the waves go by, and that person then counts the number of waves that goes by per second. That's the frequency. That's the same thing as the frequency of simple harmonic motion as well. And then the time necessary for one wave to go by, that's the period. That's also the same thing as the period of the simple harmonic motion associated with each individual oscillator. Okay, now I'm going to go ahead and start to reference some of the problems that I'll be working through in my lecture videos to be recorded a little bit later on. In order to do so, let me once again go ahead and put this back to its starting point, like so. And then I'm going to go ahead and let one wave propagate. So set this into motion. And then we'll take a look at a nice clearly delineated cosine curve here in just a moment as I pause it, like so. And then from here to here is one wavelength. This right here is the wavelength that's usually referred to as lambda. That's the distance from crest to crest. Okay, what I have right here is just a single cosine curve. And now I'm going to set this into motion. And when I do, I'm going to let it propagate such that 1/4 of a wavelength goes by. When that happens, each individual oscillator undergoes 1/4 of an oscillation. This then means that 1/4 of the period has gone by. So focus in, for example, on this black dot here at the top of this crest. Let me go ahead and set this into motion, like so. And then basically as I did that, I let 1/4 of a period go by. Each individual oscillator underwent 1/4 of an oscillation, and the wave itself propagated to the right-hand side here, 1/4 of a wavelength. That's the mathematical pattern that gets picked up as a wave propagates. That is, for every quarter period of time that goes by, each individual oscillator undergoes 1/4 of an oscillation, and the wave propagates to the right-hand side, in this case, 1/4 of a wavelength. So watch what happens after another quarter period, like so. And then in terms of the time that's elapsed thus far, what we have here is 1/2 of the period has gone by, and then therefore the original cosine curve that we started with here and here has propagated to the right-hand side, now half a wavelength. So let's see what happens after 3/4 of a period, like so. And then the wave is propagated here 3/4 of a wavelength to the right-hand side. And now let a full period go by, like so. And we just end up with another cosine curve here. This means that the original cosine curve from here to here has now propagated to the right-hand side 1 full wavelength. So once again, each individual oscillator underwent 1 full oscillation. When that happens, the wave propagates to the right-hand side here, in this case, 1 full wavelength.